Now that we know how to find critical values, we need to be able to determine whether or not my critical values represent the location of local minima or local maxima. In order to do that, we're going to utilize the second derivative test. Critical points do not guarantee that I have an extreme value at that point. Critical points just allow us to identify possible locations for extreme values. An extreme value will exist at a critical point, but a critical point does not always correspond to an extreme value. A critical point could indicate a local maximum, a local minimum, or it may identify something called a saddle point. So let's look at what a saddle point is. A function f has a saddle point at the point AB if in every open disk centered at AB there are points xy for which f of xy is greater than f of AB, and there are points for which f of xy is less than AB. In other words, if I'm standing on a surface at the point AB, and it's possible for me to walk uphill in some directions, but downhill in other directions from that point, then AB has identified a saddle point. Once we have our critical points, we need to be able to test them to see if they correspond to a local minimum, a local maximum, or a saddle point. This is where the second derivative test comes in. Suppose that the second partial derivatives of f are continuous throughout an open disk that's centered at the point AB, where fx at AB is equal to fy at AB, which is equal to 0. Then if I let d of xy equal fxx at xy times fyy at xy minus fxy at xy squared, we get the following. If d of AB is greater than 0 and fxx of xy is less than 0, then my function f has a local maximum value at the point AB. If d of AB is greater than 0 and fxx at xy is greater than 0, then f will have a local minimum value at the point AB. If d of AB is negative, it's less than 0, then f is going to have a saddle point at AB. And if d of AB is identically equal to 0, the second derivative test is inconclusive. Now I want to make a few comments about this second derivative test. The second derivative test depends on the quantity d of xy is equal to fxx fyy minus fxy squared. This is called the discriminant of f. A way to remember this is that the determinant of a 2x2 matrix populated with the first row having fxx and fxy in it, and the second row having fyx and fyy in it, is equal to fxx times fyy minus fxy squared, where fyx is equal to fxy, and provided the derivatives are continuous. This particular matrix is called the Hessian matrix. Now you'll notice that if d of AB is greater than 0, the surface will exhibit the same behavior in all directions. And one other characteristic to point out is that the tangent plane at a saddle point will lie both above and below my surface. So let's work an example. I want to find all critical points for the function f of xy is equal to x squared plus xy squared minus 2x plus 1. And then I want to use the second derivative test, if possible, to determine what the critical points correspond to. Fx is equal to 2x plus y squared minus 2. Fy is equal to 2xy. If I look at Fy is equal to 2xy, Fy has to be equal to 0, which means that y can be 0, and that gives me 0 is equal to 2x minus 2, or x is equal to 1. Similarly, for Fy equal to 0, x could be 0. This gives me 0 is equal to y squared minus 2, so that y could be plus or minus square root of 2. My critical points are going to be 1, 0, and 0 and plus or minus square root of 2. Now I want to determine what type of points I have. Fxx is equal to 2. Fyy is equal to 2x. Fxy is equal to 2y, and Fyx is also equal to 2y. D of xy is equal to fxx at xy times fyy at xy minus fxy at xy quantity squared. This gives me 2 times 2x minus 2y squared. I get 4x minus 4y squared. If I evaluate d at the point 1, 0, I get 4. Here, d of 1, 0 is greater than 0, and fxx at xy is equal to 2, which is also greater than 0, so that f has a local minimum at the point 1, 0. For d evaluated at the points 0 and plus or minus square root of 2, I get negative 8. In this case, d of 0 and plus or minus square root of 2 is less than 0. This tells me that my function has saddle points at the points 0 and plus or minus the square root of 2. When I apply the second derivative test to the function fxy is equal to x squared y minus 3, I will get the following result. Fx is equal to Fy is equal to 0, which tells me that 2xy is equal to x squared, and this implies that x is 0 and y is 0. Fxx is 2x, which implies that fxx at 0, 0 is equal to 0. This tells me that my test is going to be inconclusive. A quick graph shows that the function has a saddle at the point 0, 0. When I look at this, I see that at the point 0, 0, my graph switches from being a maximum to being a minimum at that same point. Now you get to try it. Pause the video and find all critical points for the function f of xy is equal to xy times e to the negative x minus y power. Then use the second derivative test to determine what each critical point corresponds to. When you're ready, restart the video to check your understanding. I first need to find all the critical points for the function, and then I use the second derivative test to determine what the critical points correspond to. F of xy is equal to xy times e to the negative x minus y power. Fx is equal to the quantity 1 minus x times y times e to the negative x minus y power. Fy is equal to the quantity 1 minus y times x times e to the negative x minus y power. Fx is equal to Fy is equal to 0 implies that x will equal 0 or 1 and y will equal 0 or 1. Plugging these values in, we find that my critical points are at the point 0, 0 and at the point 1, 1. Now I need to find my second derivatives. Fxx is equal to the quantity x minus 2 times y times e to the negative x minus y, and Fyy is equal to the quantity y minus 2 times x times e to the negative x minus y. Fxy is equal to Fyx, which is equal to the quantity 1 minus x times the quantity 1 minus y times e to the negative x minus y. My function d of xy is equal to fxx at xy times fyy at xy minus fxy at xy quantity squared. D of 0, 0 is equal to negative 1. This is less than 0, so that my function has a saddle point at 0, 0. D of 1, 1 is equal to e to the negative 4. This is greater than 0. And fxx is equal to negative e to the negative 2 power. This is less than 0, so f has a local maximum at the point 1, 1. Be sure and let me know if you have any questions about using the second derivative test to understand when a critical point corresponds to a local maximum, a local minimum, or a saddle point.